Here is my slide. First of all, I have to introduce you to a slide first, and then after that, I will show you live in the software. Topic today is high performance building design with Autodesk CFD. What does it mean high performance building? It means your building not normal anymore. You can develop your building more than a ordinary building by using the CFD. Try to simulate the flow, the air, temperature, everything. What we can help in Autodesk CFD, we do in 5 ways. The first one is that electronics cooling. The second one is data centers. The third one is lighting. The fourth one is machinery and valves. And the last one is the AEC, mean architecture, engineering, and construction. In electronic cooling, we can simulate the temperature and flowing the air inside the electronics component, electronics devices, and see what's going on inside, because we can't see the air by our eyes, right? The visibility is 0, right? But we can use the software, try to simulate and see the characteristic of the air inside the building or the devices, anything. For the data center, we quite seriously about the air flowing and how to dissipate the heat outside of this building, right? For the lighting as well, when light generated, we also generate heat as well, and how to reduce the cost of the thermal stress to the component. We can see. We can use our software, try to simulate and solving this problem. For the machinery and valve, for mechanical engineer, we want to see the inside of our valve, how the turbulence, flowing of the fluid, anything. We use this software to simulate as well. And for the AEC, we use in various ways. For example, the flowing, the pressure, the temperature, anything inside the AEC building, right? Yeah, that's the application of our software. For the electronic cooling, we quite focus on four topics: the airflow visualization, cooling fan optimization, improved enclosure design, and PCB board configuration. For the data center, retrofitting existing center, hot and cold aisle arrangements, evaluate free air cooling, improve airflow management. This is the example. You can see that in the data center, the heat on the top, we try to reduce the temperature inside the data center, because data center consume a lot of energy and generate many heat. And electronic devices weak to the heat, right? So if we can design the aisle to try to bring the heat upward, and then we send the heat outside of the building quickly, so the devices is safe, right? And for the lighting, we focus on 4 areas as well: heat dissipation, environment loading, improve efficiency, design simplification. And on the right side is the example. We call with many manufacturers who doing the vehicle designs and have to design the lamp or the lighting at headlight, anything. They use our software to generate and solve the problem. And for machinery and valves, we focus on flow optimization, erosion visualization, cavitation identification, thermal effects. When flowing in the valve or any devices in the pipeline, maybe there's a cavitation we can't see by our own eyes, right? But we use the software and see the characteristic of the fluid, and then we can predict variable where it can have the cavitation that's quite dangerous to our system. And we try to prevent that. We call it prevention, right? And for the heat as well, we can see that the mixing between the cold and the heat, how they doing inside the components or our device, and we can know the output prediction, how much temperature we're gonna get. And for the turbo or the vehicle, anything, the suction and the output should be in the way, in the sense that what happened, we want to see inside, right? But for the solid interact with fluid, there's need the topmost package, because CFD has two packages. The normal is just calculate the fluid only, but the topmost one calculate the solid interact with the fluid. So in turbo, there's a turbine, right? Interact with the fluid or the air or the water, anything. In the pump as well, we can see the characteristic between those. And for the AEC, we focus on thermal comfort, smoke migration, internal and external airflow, natural ventilation. For the last topic, natural ventilation, quite important because many architecture need to save energy, right? They would like to do the natural ventilation when design the building as much as possible, because forced ventilation consume energy, right? As it's not save the world or save the money of the owner or the building, right? For example, on the right side, you can see that on the two-story building, the living room should be cooling as much as possible. And for the top story, the second story should be cooling as well in the hot weather around the region, right? And for the city design, we would like to know the characteristic of the air flowing when some high-rise building happen, what affect the peripheral area. We would like to know. So we use our software, try to simulate the airstream, and we can see that the effect of the high-rise building affect the lower story building. They interact each other in which way. And computational fluid dynamics is short for CFD. So when we talk about CFD, it's short for computational fluid dynamics. That means it uses computer to compute, to calculate the characteristic of the fluid, right? The fluid, it doesn't limit to just air, also the water, the blood, anything. And dynamic is not static, right? They're moving, they're rotating, they're changing, conform to the time. So that means we would like to know the characters of the fluid when they're flowing, when they're turbulence, right? By using the computer to calculate that, the meaning of the CFD, and create multiple design iterations from Revit and compare design choices. That means luckily under Autodesk umbrella, there's a Revit and Inventor and Fusion. That's a modeling tool to send the input to CFD, because CFD itself can't do the modeling much. So it has to use Revit, Inventor, and Fusion to help in 3D modeling first, and then send the model to the CFD itself and calculate. That's the luckily that we have all of those under Autodesk umbrella. So we just purchase just one vendor. That's our lucky, right? And the second one is analyze airflow and thermal behavior. Yeah, that our main function in the software. And the last one is optimized placement of building system to improve efficiency. So this one is important because when you design or you are designer or engineer, design engineer, you would like to see that on the left, on the middle, or on the right is the best position when you place something, and would like to affect the building as much as we want, right? So we use our software, try to simulate many scenarios, and we can discuss and we can making decision easier. Typical AEC model study with simulation CFD. This is a case that we used to do in mechanical ventilation, HVAC, factory, data center, hospital room. In hospital room, when they're doing the surgery, right? The air flowing is important because air flow with the germs, right? Normally, the air should be going smoothly from input to output. Do not circulate in the room because it's quite dangerous to the patient, right? So we use our software to design the hospital room or surgery room that can save the life of patients, and also the office spaces that we would like to make it cool, thermal comfort for everyone in the building. For laboratories, clean rooms, smoke extraction, chemical spill control, thermal comfort, solar loading, condensation on windows. This one is important as well. Normally, it's not the main function of our software, but we try to use the parameter in the software, try to predict the condensation on windows in our system. And also the drag force, we use two software, Inventor and CFD, try to simulate the drag force when strong wind pass through the building, right? They generate the pressure, and we know from the engineering formula that pressure can convert to the force. So we know the drag force easily once we know the pressure in the software, right? For external flow, we loading and smoke exhaust, flow control on environment and fences, walls and courtyards. You can see on the middle picture, the air stream flowing and go to the building and then move on the sideway and flowing. We will simulate this kind of in our software next. And natural ventilation is passive building comfort studies, large atrium, condensation, and internal-external combination. You can see that in the atrium, there's a lot of seat. When you're doing the ventilation, you should get everyone thermal comfort. Otherwise, some area is hot, some area is cold. Too hot and too cold is not good in our design, right? So we would like to make every average level of cooling for everyone in the atrium. For the Revit, normally Revit has the functionalities to design development, detail analysis, and visualization, but we can't know the exactly of the fluid flowing in the HVAC system or in the building. We cooperate with CFD by importing the Revit model, but the one that we need is our must be simplified model. Do not get the full detail building in Revit and dump that data to CFD directly is not possible in the Windows system, right? Because too big file that cause a lot of problem. So we need the simplify. So you have to make two models, the one that detail too much for your work, whatever. But for the simplified model, send to CFD that our choice because the limitation of the hardware and the Windows system. So we have to use this way. It's a best practice. And CFD try to simulate and visualize data and optimize design. Optimize is important because you're not doing over or under design. So we design as an optimum level, right?
Of their building designs at the earliest opportunity, and to identify strategies to mitigate risk, ensure compliance, and improve operational efficiency. The trend is towards more companies adopting simulation in-house in order to meet these requirements. Autodesk CFD works directly with the native building design data in Revit, enabling the engineer to simulate as they design within their BIM workflow. Autodesk CFD can assess the indoor air quality to ensure air within the occupied space is replaced with the required number of air changes per hour. This prevents the buildup of pollutants in the space. MEP equipment such as air handling systems can be represented to accurately simulate the movement of airflow and to provide critical data to the MEP engineer on the optimum location of the ventilation systems to minimize on running costs. Different ventilation strategies can be quickly and easily assessed, as we can see here in this hospital operating room example. In addition to visualizing the airflow, the engineer can also assess how both the airflow and temperature can affect occupant comfort levels. Heat from radiant sources, hardware, the sun, and even the occupants themselves can be taken into account. Engineers are often required to perform fire and smoke simulations for compliance purposes. Autodesk CFD enables the engineer to simulate the movement of the smoke in a specific fire scenario and to ensure occupant safety. The position of make-up air units can then be optimized to prevent over-design. External wind studies can be used to assess the influence of new buildings on the airflow at street level in urban corridors for pedestrian safety and comfort. From a thermal perspective, the effects of solar shadowing can also be assessed at different times of the day. The use of Autodesk CFD to provide guidance in building design has also extended to factories and data centers, which are the largest consumers of energy. Engineers are able to assess and analyze different energy change measures, such as hot aisle or cold aisle containment, and the intelligent placement of ceiling or floor tiles.
Buildings today are a combination of art and science. Certainly dramatic architecture creates wonderful spaces, but there's also intense science behind what goes into making a great building work and operate efficiently and effectively and provide that comfort. At GluMac, we use BIM as a tool to achieve maximum sustainability on the projects. And the way we do that is through the energy modeling and the interaction with the Revit model, through the CFD modeling and the interaction with the Revit model, and doing it in such a way that we can minimize the capital expenditures while still proving and achieving the energy efficiency and the comfort that's critical for the operations of the facility.
GluMac is an engineering firm that's very well known for its commitment to sustainability. We've been doing it for over 40 years, and we have experts that are experts not only in sustainability, they're experts in market sectors, and even in design practices and technologies like building information modeling, computational fluid dynamics, and energy modeling.
When Dick GluMac first started the firm, it was really just called efficiency, not sustainability. Where today's sustainability is looking at what are the most efficient, best methods for designing a building, what are the mechanical, electrical, and plumbing systems, and ultimately sustainability is intertwined with economics and energy efficiency.
In the past, when we did advanced calculations such as computational fluid dynamics or energy analysis, daylighting simulation, we had to completely design a separate model from scratch. Now, with building information modeling and a platform like Autodesk Revit, we can now use the same model for both applications.
We're able to take that same geometry and use it for energy analysis. We're also able to put it into Autodesk Simulation CFD, or even take it out to third-party tools. At the very beginning of a project, we'd start with Autodesk Green Building Studio, and that would allow us to do some of the first runs and initial performance metrics. Then once we got into a little bit deeper, we'd start moving into the other Autodesk building performance analysis tools. And that would allow us to refine the energy analysis and do more detail on the big picture system options. What Autodesk Simulation CFD would allow us to do is look at how those systems are operating in terms of the airflow and the space and the comfort. We've used Autodesk Simulation CFD to evaluate the parking garage at Wilshire Grand so that we can design the fan systems to operate more appropriately to the specific end-use need so that we have a safe environment. Energy analysis and Revit offers us the ability to do all of those test runs and initial studies up on the cloud without compromising our local servers and storing all those excess files. Plus, when we start to do multiple iterations and different evaluations, we can do all of those runs on the cloud, freeing up the demands on our local computer.
Sustainable design has always been equated with more cost, or people anticipating that it's going to cost more to save more in the long term. But now with technologies allowing us to create more iterations of our design, we're coming up with better designs. Our designs are more sustainable, we're saving more money up front, and doing it in a way that's cost effective not only during the design, but right away for that customer.
When you're involved in the concept phase of a project, you want to evaluate all the different alternatives, the shape of the building, how the light comes into the building, all of these different parameters, and you want to test that very, very quickly in the concept phase and understand how that's going to impact energy. And if you have these tools at your disposal that can generate these in a period of days and feed that back to your clients so they can be informed on their decisions about how their design will affect the overall operating costs, the comfort in the space, this kind of information really is invaluable. And as a business, it's allowed us to differentiate ourselves from our competitors. We're no longer commodity because we provide expert advice and expert consultation, and we do it very cost effectively using technology to assist us. The future of BlueMac is to continue to invest in technology, and we partnered with Autodesk and Revit to really advance the construction industry. And Revit's helping us get there in a way nobody else can.
Okay, we will switch to our software. First of all, I would like to model something simply. I don't want to make it complex, and try to explain the basics or the functionality that needed in every simulation. So I use this house. I model it in the Inventor. For example, how to model this house, I will explain you quickly by using this tool. The important is that the axis on the system, you have to be careful because in CFD itself, I try to open something here. You can see that there are z-axis pointing up. So when we modeling something in Inventor, we try to make it on the XY plane here. And when we using the function, try to make the rectangle at the middle, we tie this 6m, that means 6 meters in length. And this 3m is mean 3 meters in length as well. And this is our house. And then I finish and extruding this one. For example, I would like to make it 3 millimeters in height. And here we go. We got this one easily, right? And then the second one is that I extruding on this face. And then I try to make it the roof by using the rectangle function here. Try to make this one. And then we want to get rid of this slide and try to destroy the parallel function and make this one go further to meet each other at the middle. And then I use the alignment tools this one coincident on this line, and then I make it dimensioning here from here to here about 8 meters in length. That means I have this one, the midpoint of this one to midpoint of this one, and the height of the roof around 1.5 meter. Finish, and then extrude this one. Try to meet at the back by using this function. Click on this one and OK. Here we go. What we get is that the house, simple house, right? Okay, switch back to my simple house here. I would like to send this model to CFD by going to the simulation. Once we install, the trick is the first thing I have to install is Inventor. And the second thing is that CFD. When CFD install, it adds the function to Inventor. So I just click the active model. That means send this current model to CFD. CFD going to be launched, and then try to name this one. But I use the default name and then launch. Easy like this. And we wait for the CFD to run. I try to show you the simple thing. Here, you can see that the house coming with the right direction. Here we can use the function or the view queue in Inventor as well, same in CFD. And then we use the geometry tool. So the flowing, normally there are two types. The first one is external flow, and the second one is internal flow. For example, in this case, I would like to know the external flow. So I go to the geometry tools and then external volume. The function to model external volume, there's included in CFD already. You don't need to decide the external volume in Inventor, just the simple house. And there's an external volume in here. So I try to roughly design, move arrow to the front, move arrow to the back. And there's a top, right? I would like to position this volume in the middle of the house. So I use this one, not exactly, but roughly in the middle, right? So we don't need the exact location, because we try to simulate the volume, the closed volume. Because why we need the closed volume? Because this volume gonna be fluid. So we can't do the infinity volume because it needs the much function in computer, consume a lot of energy. That's not good in the software, right? So we try to simulate some area to be the external volume and then create. This volume create easily like this. It's called enclosed volume or external volume. And then the second thing, you need to know that software needs 3 input. The first one is that geometry, that we have a house and the external volume. You can see here 1 and 2. The model already input here. And then the second one is the material. So we need to set the material that the second needed input, right? So on the house, I right click and edit. Try to make it solid. You can see that the type of the material for the model, there's a lot, right? There's a fluid, there's a solid, resistant, internal fan pump. Because my software is Ultimate, so the topmost package. So I have all of the setting, right? But when we use the lower package, maybe some centrifugal, something is missing, right? Because it's all the fan pump, you won't get this function in the lower package. So In this one, you can see that the heat sink, check valve, or anything. But right now, in this case, my house gonna be solid, right? And I try to apply the brick material to the house and apply. You can see that the unassigned, once you see the unassigned, you can't go to the solve function, because once you click the solve function, the software won't allow you to do. So you have to assign all the material first and then edit, making the fluid and air. Okay, and then apply. For the material, you can't see the unassigned section. That means you can go further to the boundary condition. For boundary condition, you click on the phase. This phase gonna be in inlet of the air, right? You click the edit, and then you set the velocity of the air. In this case, I need 20 kilometers per hour. The air coming in this way, and then I see the direction of the arrow is right, is correct. So I apply. That means this gonna be the input of the air, 20 kilometers in to the system. And then I rotate back to the back face and I click edit. The output is fixed in the software that it's gonna be pressure 0, gate pressure at 0, apply. That means this phase gonna be output phase, and then completely assign, then go to the solve function. You want to save the step, how many interval? Start from 10 interval, and then continue from 0 to 100 iteration to run, and then click on solve, and we wait for the result. You can see that the system run at the bottom, showing the graph flowing, going further, and you wait until it's going to the 100 iteration. This means the iteration and get the data by the software showing the progressive. You just wait to the 100 iteration. Once finished, you can see that the result, the output gonna be analysis complete successfully. That means you can close the output bar or minimize the output bar here. Try to maximize your screen, and then use the function. Try to analyze or see the result by clicking on the plane and then add. This is gonna be the section at our house. The blue one is mean the section of our house. You can see that the silhouette of the line, that's our house, right? And this one gonna be at the middle. You can use the arrow to move to see the section. When you don't want this plane anymore, you just click on the remove, or you want to get rid of all of it. It's gonna be remove all. And you try to add as much as possible. When you want to do the 45-degree angle or something, or inclined plane, you can rotate the plane to do to see the section wherever you want. And then I try to remove this one. I want to add the new one here. And then I would like to place the plane at the middle of my house in this direction. We call this is the X plane because it's cut at the X axis, right? And then I add more, and then I click in this one. I want to perpendicular to the Y axis here. And then I add more. I would like to make it perpendicular to the Z axis here. So I have this three plane, try to cut at my house and see what's going on in our model. And this is gonna be three plane. In the section of the plane, I can hide any plane I don't want. I can hide this plane and hide this plane first, and I can bring it back or resume the plane whenever I want. And then here you can see that the output is showing the red color and the blue color, right? And on the left side, you can see that the velocity magnitude. That means this color gonna showing the velocity magnitude in kilometer per hours. That means in this area it's quite red. That means it's close to 24, the maximum magnitude, around 20 kilometers per hour. And on the blue, it means 0. That means in this area, the velocity close to 0, right? Because it's in the, or maybe 1 or 2 kilometers per hour. So that's quite slow wind, right? But you can't see it exactly because just the color only. When you want to see you click on the plane first and show the vector to see this direction that the air flowing. You see that the air direction is indicate the direction of the air flowing to the house, and then when touch the house, it's gonna push to upward, right, at the top, and then flowing at the bottom, it's gonna flow down, right? And then you need to see vector setting, try to find the vector, right? Or course is mean reduce the number of the arrows, and phi is mean adding more arrows. Try to see, right? You can see at the back of our house is turbulence. Here the air is flowing circular, right, in this area. So the next thing that we want to see is the pressure. We can see the static pressure, and for the vector, we don't want to see none. Here you can see that when the air is coming to my house and touching the house, it's gonna create a lot of pressure on this plane. That means when we forcing the air flowing or in the tornado, right, we can face the wind directly because it's gonna create a lot of pressure. So we have the wind push us to the direction of the wind, right? In this house, it's gonna resist the wind, right? So create a lot of pressure. In this area around 20 Pascal. Not much because the air flowing just 20 kilometers per hour, quite slow, right? But the software showing the color. So it doesn't mean that red is dangerous, no. Blue is safe, no. It doesn't mean like that because it's showing the maximum on the positive, right? And this blue show maximum in the negative. But this one, you can see that the pressure is negative pressure. That means on the roof, it's gonna be sucked by the wind, right? The wind gonna suck this roof upward. So if your structure of the roof is not strong enough, maybe your roof gonna destroy by the wind because it creates the negative pressure at the top of the roof. Here you can see. When you want to know the exact number, right? What's going on in how much of the wind pressure at here? Try to use the XY plot function, and then you create add by picking add point. You quite interest in this area, right? And then create a plot. You can see that the graph gonna showing width die per square centimeter. You can right click and create change the unit to pressure in our area. Use Pascal, right? Pascal. So the maximum in this area is gonna be 26 Pascal here. And you can make a decision it's dangerous or not with 26 Pascal. I think it's quite safe, right? So, and we would like to save the data in the Excel format? Yeah, we can do. So I wind pressure. I want to save in wind pressure here. And then I want to save again and try to open by Excel to see the result that we get from the software. Here, you can see that a lot of information get from the software, right? And you try to use this function, right click and column width around 20. Okay, and you can move back and forth and try to find the static pressure maximum number is here, 26, right? Here we go. But why is no negative number? Because you cut or you drag the line just in this portion. If you want to see all the pressure along this face, you have to use the add point again, but you have to start from the bottom to the top. That's no. This area just the positive pressure, right? This is the negative pressure that we add this instead in this area. It's cut to the blue area, right? And then we plot. We're gonna see that there's a negative pressure here. Apologize for the first because this is the positive. You see the red color, right? This is a negative, the blue area. So we have to cut through the blue area here, and we can see that its negative pressure is minus negative 14, negative 13 something, but we can round up to 14, right? Negative 14 in this top of the roof here. We can know exactly the number by using XY plot. Try to plot in the area that we quite focus on. And then when we want to make the summary, we click on the make summary and going to the decision center, update all. And we can see that the plane that we cut to the house, there's a lot of information, not only the pressure, but the area, the density, the pressure force, scalar. Pressure force means the drag force, right? The unit is die. When you want to see the Newton, you just change the unit. And you can see that 511 Newton pressure force on the area at the top of the roof, because you have to know exactly where you cut the XY plot or the function. Okay. Here's an overall picture how to use the software, right? And the next thing that I would like to show you is that I want to make this plane, try to set up and result back here. I would like to click on the plane, and I would like to parallel, align to surface. That means parallel to this one. And I would like to see the next output, that is traces. We can make the traces density around 20, and then I add from here until here and up to here. We can see the vector or the streamline of the air flowing interact with our house. You can see in this line, the air flowing upward, because the house is blocked the wind, right? Wind have to find the exit. So the flowing upward, try to avoid the house, right? And you can see the animation here. Try to see. You see the air flowing like this. This one is quite smooth right? Because it's just the normal flowing, not circulate flowing like in the valve. So in the valve, maybe it's quite turbulence inside the valve, right? But this external flow is quite easy. Okay, this one. Any questions from you guys? No, right? Okay, I would like to showing more about the ventilation pipe. I would like to create the model again here. I would like to create, as I told you before, we focus on this plane here. We would like to create the line or something from here to here, around here. This is the cone, right? This is a cone. I would like to make it dimension around here and finish. I would like to rotate this one here. And I would like to send this model to CFD easily, right? I go to simulation. This model have to save first, and then I save the model as cone, and then active model, send this model to CFD, right? And then the type is cone and launch. And wait for the CFD to launch. It read the model, right? Here, our cone pop up, easy like this, right? It's direct integration in both software. And then I set this one, gonna be air fluid, air apply. And then I going to set the boundary condition, going to this about 10 kilometers per hour or meter per second. It depends on your choice. In this, gonna be 2 meters per hour, 2 meters per second. Okay, apply. And then for the output, as I showed you before, the pressure 0. You have to remember this because it's quite the fixing information, right? Pressure 0 is output, and then solving. I don't want to keep the result anything, just showing the exact. And see, because the simplify the model, the software calculate faster, right? And then we can make the plane cutting through. We like the plane around, perpendicular to y-axis here. Okay. And here we go. We can get the information of the section when air flowing through the cone, and then we can see that the output is quite faster than the input, right? And then I had to remove and then see the exact area. This one, delete first and go to the boundary condition again. Maybe we didn't clear the selection yet, so I try to assign again, apply. Okay, this one, try to show again. Yeah. Okay, try to make the plane and add. Okay, this perpendicular to the y. Okay, this one is right. Because I have misassignment on the boundary conditions stated, and then here's exactly what's going on inside our cone when air flowing inside, and output it here. When we want to simulate not the air, but we want to see the water, right? I like, let's say it's a reducer when the water coming in and going out. I try to set the fluid to water instead. Once we change something, water, can I, please give me a moment, try to see water. Okay, see water or gas phase or fluid phase, right? This is seawater fluid phase, and then applied. And then once we change something, we have to solve again. This one you have to careful, start from 0 and solve. Yes, we want like to overwrite the old data and see what's going on again. And then we go into the output plane and then velocity here and showing the final, the velocity, right, vector, because it's a big chunk of cone, right? So maybe the vector is quite small. How to solve this? We go into the vector setting and make it bigger in length, right? Bigger size of the arrow, and try to adjust the number of the arrow. Try to see it easily as we want. And we can see that the air flowing from the cone to the output, from the input that's big to the output that's quite small. We know from the physics that the air is going to be faster, right? We like to see, we like to read the number of the changing. We go into the peak from start until the end. What gradually change? It changed from we change to kilometer per hour for easy understanding, right? 37, roughly 37 kilometers per hour, and from the start point, it's close to 10, right? 7 kilometers per hour at the middle, and changing the speed to 37. From 7 to 37, quite much, right? Quite much of speed increase. But it's a physics, you know, because this is the physics. It should be like this. So that means this one gonna be changing the speed because you reduce the cross section. That's a physics, right? Here's is conform to the physics rules. And then we get back to our house. And if we want to simulate the internal flow here, internal flow is working like this. You create the model and then flowing simulation inside, we call internal flow. But this one, you seeing the flow around the house, that means external flow. So you have to create the geometry tools in here, external volume, right? For the model that have the hole, you can you use the void fill to close the hole, because we want the closed system. That's our rule to remember. All the model have to be closed. It can't allow the hole happen. For example, the valve with the open hole, it can't be used in our software. We have to close the hole, but we want to save your time by using our geometry tool to void fill instead of getting back to the CAD software and fill the hole. By the CAD software, again, that's quite take time, right? So this one has the geometry tool, but is just limit to the void fill and external volume as small object, get rid of, simplify the model with small object, and edge merge for your CAD that doesn't good in modeling. Maybe it has the open gap. It's gonna be edge merge to help you close the volume. That's the meaning of our flow function in the software, right? And you can use this option, try to simulate the navigation. In this case, I would like to mimic the other inventor control. But you can, if you're familiar with Revit, you can change the control of your mouse like a Revit. So you can use this software quite easier. So in the default, it's going to use this CFD instead, but you can change on the fly to Inventor or Revit, whatever. Or even you use a reverse or you GNX, you can Pro Engineer, you can use the control like your favorite software. That's our functionality added to help you use the software easier. And for the setup unit, you can use the default. For example, when I ask to set the velocity, the default going to be kilometer per hour. But if I prefer to use the meter per second, I set the default unit to here. And system gonna remember this. And once it getting setting to ask you, it's gonna act by meter per second to save your time to offsetting like this. And for current and voltage to ampere and volt or kilovolt or millivolt, that means you can simulate in the level of high voltage to the electronics level. So it's quite widespread, wide application to use in our software to help. And then for the result unit as well, when you want to read something, for example, you want to read the velocity, you quite prefer this kilometer per hour to getting understand. You can set the default unit of the results in here and the pressure to Pascal or megapascal in the high pressure. You can change like this. It's quite easy. For the temperature with Celsius and another unit as well, but it's quite specific unit for the architectural field, right? Here, the overall picture of our software. So back to our slides. And then you can see that we have the application to use here. For the model complexity, we don't need, right? Because this one is quite complex. So we simplify the model. You can see that the cabinet gonna be simple block. And then the people or the doctor or nurse should be in the simplified model of the human. And for the lighting, anything gonna be cylinder. That's our need in the software. We don't want the detail. For example, the monitor or the computer, anything we don't want. You just simplify it as a simple block. Simply say that reduce the phase of the model. Phases of the model is importantly related to the time of calculation. And for the single side ventilation, you can use our software, try to flowing air in and getting air out, and try to see the inside of the room is flowing good or not. Or cloth ventilation, stack ventilation, what the application that you would like to do. And for in the YouTube, there's a lot of information and video showing how to use the software. I assure you that once you listen to me in this webinar and once you go to the YouTube, you will understand easier than before because you have seen my simply explanation, right? And this slide gonna be on your hand after this session end, so don't worry about it. I added many videos inside as well. Okay, go to the Q&A section.